Oh no, it's okay. So I don't think Elliot can hear me. So it has to be on Elliot's end. Oops. Well, sorry, Elliot. Here, let me try this. All right. That is weird. All right. Well, I guess I'll go ahead and keep going then. I'm sure Elliot already knows all this stuff. So yeah, that's unfortunate. So the gradient of f at xyz at a point xyz is the vector in space given by, and then we write it this upside down delta f xyz is equal to the partial of f in respect to x at xyz, the partial of f in respect to y at xyz, and the partial of f in respect to z at xyz. Okay. You could also write this, the easier, more compact notation, right? It's just, f sub y, x, y, z. And the same thing holds for if your function maps R2 to R, then this is R3 to R, so R2 to R, del f of xy just be, partial f respect to x at xy, partial f respect to y at xy. So this is exactly, so think of the matrix of partial derivatives, but it's written as a vector now. So, oh yeah, this, you can pronounce it del f. Del f, the del operator is what it's called. Okay, starting out with the definition, we have the directional derivative. The directional derivative. So if f maps R3 to R, the directional derivative of f at x along vector v is given by let's see. So limit as t approaches 0, f of vector x plus t times vector v minus f of x over t, right? Just synonymous to the difference quotient, where v is a unit vector. Okay, so what is the difference between a directional derivative and a partial derivative? Well, so if we have, let's see, some surface. Oh, so like if we think about what f sub x is doing, the partial of f respect to x, that's like, at some point x, and we keep, y fixed, and we take, a small, just based on the definition of this this partial derivative, we take a small step in this direction, in the x direction, right? Because we had, oh, it was the limit as, like, remember this already, f of x plus t comma y minus f of xy over t. So this partial derivative is the same thing as the directional derivative, except it's the directional derivative in a specific direction. It's the directional derivative if we use v as the unit vector 1, 0. And then if we were to do, f sub y, partial f respect to y, well, this is a limit as t approaches 0 of f of x y plus t minus f of xy over t, where this could be written as a directional derivative where v is equal to 0, 1. Notice it's a unit vector. The magnitude of v right here is equal to 1. Same thing right here. Magnitude of v is equal to 1. So yeah, so the directional derivative is now generalizing the notion of derivative in multiple variables. Functions that map, in general, f maps r into r. Okay. So now we can take directions. We can take derivatives in any direction we want. So let's have a theorem. If f maps r3 to r, it's differentiable, then all directional derivatives exist. The directional derivative of f at vector x in the direction of vector v is given by d sub d sub v f of x is equal to the gradient of f dot v. So you would, take your partial respect to x, evaluate it at x, y, z, and then dot it if v is equal to something like a, b, c, where the magnitude of v is equal to 1, times a is the x component, partial f respect to y, x, y, z times b plus partial of f respect to z, x, y, z times c. Now, I'm not going to prove it, but the proof does involve you define a function of a single variable h, and h is dependent on x, y, and z. No, something like that. And then you would use the chain rule, and the chain rule for multiple functions of multiple variables. Yes, it's in the book. I'm not going to bore you with it. So we have a theorem. So this last theorem, this is like, how you calculate it like realistically. Like, every time you could use this definition, but I mean, think about it. When you calculate any derivative, you don't use the limit of the difference quotient besides like the first time, And now we have this nice theorem where if we want the directional derivative in a specific, a derivative in a specific direction, we just dot it with the gradient, so long as v is a unit vector. So now we have another theorem. So suppose del f of x does not equal 0. Then the gradient of f. I hope you can hear me, Elliot. Gradient of f at x points in the direction. Along which f is increasing. Sweet, awesome, cool. Is let's see, increasing the fastest. So the gradient of f points in the direction along which f is increasing the fastest. And I'm going to provide an explanation to this. So say let v be a unit vector. And then suppose we take this directional derivative in the direction of v of f at x. Okay, so this is equal to, by the above theorem, del f x dot v. Okay. Now we could take the dot product as we normally do, the easy way, where we just multiply component wise. But instead, I'm going to use the definition. That is the magnitude gradient of f times the magnitude of v times the angle between them, the cosine of the angle between them. That's just the definition of a dot product. Okay, but remember, v is a unit vector. If v is the unit vector, then the magnitude of v is equal to 1. So this is equal to the magnitude gradient f at x times 1 times cosine theta. Okay, now think about this expression real quick. It depends on theta, right? Suppose x is a fixed point, then if theta is the angle between the vector gradient of f at x and vector v. So to maximize this expression, what must the value of theta be? Jasmine, are you in this class? Are you taking? 0, yeah. Okay, cool, yeah. You're perfect, correct. Yeah, it is 0. So theta must be 0 degrees or 0 radians, right? Same thing. So that cosine of 0 would be 1. On the other hand, what value of theta minimum this expression? Remember that the magnitude of any vector is always positive. Let me check. What do you say? 180 or pi. Yeah, exactly. The other direction. Very good. So let's see. So this is maximized when theta is equal to 0, implying that cosine of 0 is equal to 1. So the directional derivative is maximized when v and the gradient of f of x are parallel. So that means that the gradient of f points in the direction of fastest increase. All right. Now let's do some calculations, y'all. Let's calculate some stuff. This first one, so we're given a function. Well, they give us the answer in this one. We just have to show it. So they say show the directional derivative of, and they give us a function of 3 variables: f of x, y, z, is equal to z squared x plus y cubed at the point 1, 1, 2 in the direction of vector 1 over square root of 5i plus 2 over square root of 5j is, so the directional derivative at this point in the direction of this happens to be a unit vector, is 2 square root of 5. Okay. Now, like I said, the first time we're going to use the standard definition of the directional derivative. We're not going to use the dot product definition theorem because, to show the validity of the definition, you can verify if you want. If you take the product of the gradient evaluated at that point with the unit vector, you would get 2 square roots of 5. But right now, we're going to use the definition. We have the limit as h approaches 0 of, and then it was, let's see, f of x plus tv minus f of x over, let's do t, over t. Okay. So what is v? What is v? V equals what? Tell me. Yes. Now, notice they only gave 2 components. It should actually be 3 components, right? They just say plus 0k. Yeah. 1 over square roots of 5, 2 over square roots of 5, 0. Okay, so like this guy, this monster, is going to be the limit as t approaches 0. And then we're going to do, let's see, so this, if you expand this x, this vector x is really, like x naught, y naught, z naught. And this is like x naught, y naught, z naught. Okay, so this is going to be the limit as t approaches 0 of f of x naught plus t times, and this is called this like ABC, plus ta, y naught plus tb, z naught plus tc, minus f of x naught, y naught, z naught over t. All right, so let's see, x is 1, y naught's 1, and z naught is 2. T is just t. A is 1 over square root of 5. B is square root of, there's 2 over square root of 5, and c is 0. So we're going to have this expression turning into the limit as t approaches 0, and then we just plug in x naught plus ta, y naught plus tb, z naught plus tc into f. Okay, so we have z squared. Well, z squared, that's going to be 2, or z naught plus t squared is 2 plus t times 0 squared. Then we have, x naught plus ta to the first. Well, that's going to be 1 plus t over the square root of 5 to the first, plus that's a y cubed. So we're going to have plus y naught is 1 plus 2t over square root of 5 cubed. And we're subtracting off f of x naught, y naught, z naught. Well, that's just 1 squared times 1 plus 2 cubed. Plus 1 cubed. The 2 is z, so that's 2 squared. Yeah. Okay, my bad. See, z is 2, y is, so cube, yep. Okay, and then divided by t. So now it's just going to be a matter of, foiling this expression out on up here. So this is the limit as t approaches 0. Well, this t times 0 is just 0. So this is really just 2 squared right here, which is 4. Right, so we have 4 plus 4t over square roots of 5 plus, and then we have to cube this animal right here. Cube that animal. So that's going to be, let's see, it's going to be 1 cubed plus 1 squared times 2t over square root of 5 to the first plus, let's see, that'd be the first times 4t squared over 5 plus that animal cubed 8t cubed over 5 root 5. How did I do that? Well, I'm glad you asked. 2 square root of 5 cubed. So I just use, a plus b cubed is equal to a cubed plus 3a squared b plus 3. Oh, there's 3 there, isn't there? All right, 1 so times 3 times 3. This is binomial expansion, right? Plus b cubed. Yeah, that's perfect. All right. So, and then we have minus, see, that's minus 4 minus 1. All this divided by t. Okay. So, good thing, good news, stuff cancels. We have this 4 right here, negative 4 cancel. We have positive 1 and negative 1, those cancel. And then we have, let's see, what do we have? We have the limit as t approaches 0. Okay, so these have the same denominator right here. And this is 3 times 2, which is 6. So we have 4 plus 6t over square root of 5. So that's 10t over square root of 5. Plus, we have 12t squared over 5 plus 8t cubed over 5 square roots of 5 divided by t. So this is equal to, well, this t cancels with this t, cancels with one of these. Now we have 2 of these left over. So then we have the limit as t approaches 0, 10 over root 5 plus 12t over 5 plus 8t squared over 5 square roots of 5. Okay, we'll just apply the limit here and here. Goes to 0, goes to 0. Well, what is 10 square roots? 10 square roots of 5. There's no t in there. Multiplied by root 5 over root 5. So this is 10 root 5 over 5, which is 2 square roots of 5, which is what they asked us for. So we have shown it the long way. All right. Now that that is out of the way, let us do this in the easier dot product form. Okay. Let's do an example. Example. This is the next few problems are just going to be simple calculation, just questions given a function of 2 or 3 variables. Just calculate gradient and then take the dot product with the unit vector. I'm also going to ask you what's the maximum rate of change and what direction that rate of change is in. Okay, so compute directional derivative at point in given direction. So we have f of xy is equal to x plus 2xy minus 3y squared at x naught, y naught equals 1, 2. In the direction of v is equal to 3 over 5 over 5. Okay. Is v a unit vector? Is V a unit vector? Okay, so we have magnitude of V is equal to the square root of 3 over 5 squared plus 4 over 5 squared. This is equal to the square root of 9 over 25 plus 16 over 25. 9 plus 16 is 25. So we have the square root of 25 over 25. Square root of 1 is 1. Therefore, V is a unit vector. So we don't have to do anything to it. Yeah. So you have to check it. Yeah, I mean, you do, or you could just, after enough experience, just probably able to recognize. Like with that first one, you could tell it was, a unit vector right off the bat. And this one is also a unit vector. So we don't have to do anything to it. But, it's probably wise to check every time. So let's write our formula down, our little theorem. We had the gradient del f at xy dot v is dvf at x. Okay, so let's calculate the gradient. What is del f of xy? Okay, well, it's a vector. It's a vector of partial derivatives. So we have, let's see, we have partial f respect to x, partial f respect to y. Partial f respect to x is going to be 1 plus 2y. Partial f respect to y is going to be 2y minus 2x minus 6y. And then we evaluate this at our point. Directional derivative, or the gradient at the point. So at 1, 2. It's going to be 1 plus 2 times 2, 2 times 2, no, 2 times 1, minus 6 times 2. Okay, well, this is 4 plus 1, that's 5. And then this is 12, a negative 12 plus 2, it's going to be negative 10. So this is, del f at 1, 2 is equal to 5, negative 10. Okay, now all we have to do is dot that with vector v, unit vector v. So we're going to take 5, negative 10, dot product with 3 over 5, 4 over 5. Okay, so we get 5 times 3 over 5 minus 10 times 4 over 5. 5's cancel, so that's just 3. And then 10 cancels with 5, we get a 2 on top, so 3 minus 8, negative 5. So that's the directional derivative. That's dv f 1, 2 is equal to negative 5. Okay. I'm going to ask a question. What is the maximum rate of change at 1, 2? Yes, very good. Yeah, so the magnitude of the gradient vector, magnitude del f at 1, 2, just so happens to be the square root of 25 plus 100, right? Because that's 5 squared plus negative 10 squared. the square root of 125. Well, 125 is the same thing as 5 times 25. And so we separate the square root, we get 5 square roots of 5. That's the maximum rate of change. And then the minimum rate of change would just be the negative of that. And then in what direction? When someone asks you in what direction is the maximum rate of change, they ask you for just direction, so you should answer with a unit vector. Though, the gradient does point in that direction, you would just have to normalize the gradient to answer that question. So say max rate of change in what direction? In what direction? Well, that's going to be del f 1, 2 divided by magnitude f, del f 1, 2. So that's going to be 5, negative 10 divided by 5 square roots of 5, 1 over square roots of 5, negative 2 over square roots of 5. Okay. Now another calculation problem. So we have f xy is equal to log square root x squared plus y squared x naught y naught equals 1 2 or 1 0, and then v is equal to 2 square root of 5 1 square root of 5. Is v a unit vector? Does the magnitude equal 1? Yes. Very good. So now we have to take partial derivatives of this animal. What is the derivative? What is d dx of logarithm, log base 10? Well, I was about, oh man, this is a couple years ago. So like technically, I can't even remember anymore, but so like d dx of like, ln, the natural log of, say, u, was, u prime over u. But when you have a different base, right, this is base 10 versus base e, it just changes it by a scaling. I think it's u prime u times ln of 10. Yeah, that makes sense because like the change of base formula. So we know that log base 10 from algebra is equal to the ln of u divided by the ln of 10. Well, this is just a constant, so that can hang out front. We take the derivative of this, and this is 1 over, or u prime over u times 1 over ln of 10. But I was in, this math class. It was multivariable. It was a vector calculus class, but doing this same stuff. And the question came up, like, the derivative of a logarithm other than log base e. And the TA was just like, yeah, just count it as, as if it was natural log. From that point forward, no one has corrected me on it. So I guess that's what they do after a certain point. They just get about this constant right here and just say, well, derivative of a constant is constant times the derivative, so it doesn't really make a difference. So that's what I'm going to roll with on this problem. So let's calculate the gradient f at point xy. Okay, so we have u prime over u. So we have our over u, with respect to x this time. And then we have, well, this is to the 1/2 really, the square root's really 1/2. So we have 1/2 x squared plus y squared to the negative 1/2 times 2x. 2's cancel. This negative 1/2 and the positive 1/2 on the bottom are going to combine. And then we get, like symmetry across the variables. Sometimes it's nice, partial derivatives work like that. So simplifying this expression is almost we get unit vector, but this is actually not square root on the bottom. So we have that is the gradient of f if f is the log of the square root of x squared plus y squared. And let's evaluate at 1, 0. Well, 1, 0 is really easy. That's just 1, 0. So that's the gradient of f. This is del f 1, 0 is 1, 0. Now we just have to take the dot product with our vector, our unit vector is, so you have 1, 0 dot 2 square roots of 5, 1 square root of 5. So 2 over square roots of 5, 1 over square roots of 5. This is equal to 2 over the square root of 5. Because, 0 times 1 square root of 5 is 0. What is the direction of the fastest rate of change of f at 1, 0? What's the answer to this question? The direction of fastest rate of change of f at 1, 0. Yeah, you're right. It's this guy. Let's see. Yep, very good. Because this is the gradient, and then you would just, in any situation, you would just normalize the gradient. Normalize means divide by the magnitude. But this is already normalized. Notice the magnitude of del f at 1, 0 is 1, 0, which is equal to 1. So the direction of the fastest rate of change, answer as a unit vector, is 1, 0. And then what is the maximum rate of change? Of f at 1, 0. Yeah, because this is the magnitude of the gradient vector, which we already calculated right here was 1. So the max rate of change of f at any point is always going to be the del f of f at that point, which just happens to be 1 this time. And then direction of fastest rate of change, this question can always be answered with del f xy over magnitude del f xy. Okay, this one's a little bit different. Now we got 3 variables this time. So we got, let's see, we got f, x, y, z. This is like a volume function, x times y times z, right? Think length times width times height. So we have our point x naught, shorthand, just write it like that. It's 1, 0, 1. And then in the direction of this direction vector, 1, 0, negative 1. Okay. So what's the directional derivative? What is, well, d sub d f x? First of all, is d a unit vector? No, it's not. Correct. Thus, we need magnitude. Divide by that. So we have the square root, 1 squared plus 0 squared plus negative 1 squared. So that's just the square root of 2. And so we divide d by that. So unit vector is equal to d divided by magnitude of d is equal to 1 over root 2, 0, negative 1 over root 2. Okay, now del f at xyz is equal to the partial of f with respect to x is yz. The partial of f with respect to y is xz. Partial of f with respect to z is xy. Okay, now we evaluate this at our point x naught equal to 1, 0, 1. So we have gradient f at 0, 1 is equal to, let's see, y is 0, x and z are 1. So then define d, well, d wasn't a unit vector, so now it's, d sub u f x is equal to, let's see, 0, 1, 0, dot 1 over root 2, 0, negative 1 over root 2 is equal to 0. Not changing in that direction. So let's see. Those problems weren't that challenging. I saved some of the harder, lengthier problems for maximum and minimum values. So hopefully we can get through all of them. I think we're gonna try to hit 3 or 4, and also just set the groundwork for what we're gonna be doing for max and min. So now we're switching topics to max and min of functions of several variables. So, what is a local extrema? So, I'm going to talk about two variable case. So, let's say let f map d subset of R2 into R. Okay, so f has a local maximum at x naught, y naught, if for every xy in the neighborhood of x naught, y naught, we have the following. If f of x naught, y naught is a maximum, then it has to be greater than or equal to everything surrounding it. On the other hand, so f has a local minimum at x naught, y naught, if for every xy in the neighborhood of x naught, y naught, f of x naught, y naught is smaller than or equal to f of x, y. Okay. Now, let's recall from single variable calculus, right? We had critical points. So, if 1, 2, if f sub x of x naught, y naught equals 0, and f sub y of x naught, y naught equals 0, or the partials don't exist at x naught, y naught. Of course, but f is defined there. It's in the domain. So either one of these two things could happen. Either the partials equals 0, or the partials don't exist, but f is defined there. This is a criteria to call x naught, y naught a critical point. And remember, critical point does not apply maximum or minimum. It means it's potentially a maximum or minimum. There's more work to do. So say in general, if x naught, y naught is a critical point, x naught, y naught is not necessarily local extrema, a max or a min. An example of a critical point that is not a maximum or a minimum, let's just do a single variable case for now. F of x equals x cubed. Because if we look at f prime of x, this is 2x. This equals 0 if only if x equals 0. So that means x equals 0 is a critical point. But if we look at the graph of x cubed, it looks like this. So we have a horizontal tangent line, i.e. critical point here, but it's neither a max nor a min. So we have a second derivative test for functions of multiple variables. Okay, so define, it's called the discriminant, I think. Discriminant. D, say D sub f of x naught, y naught, or just D, doesn't matter. It's the determinant. It's the determinant f sub x at x naught, y naught, f sub x y, x naught, y naught, f sub y x naught, y naught, f sub y x naught, y naught. Because when you take this determinant and then either remember it like this or in the following way, how you will actually use it. If you take this determinant of a 2 by 2 a, b, c, d is equal to a, d minus c, d. So we have f, x, x, x naught, y naught, f, y, y, x naught, y naught, minus f, x, y, x naught, y naught, squared. Because right, we would have AD minus CB. Well, C, f sub yx, and f sub xy, we have equality there by Clairaut's theorem. The mixed partials are equal if they're continuous. And in this class, we're only going to be dealing with nice functions. This is our second derivative test. Well, this is the discriminant. The second derivative test actually goes like this. So if f x not x naught y naught f sub x equals f sub y x naught y naught equals 0, i.e. X naught y naught is a critical point, and then we have three cases. So if the discriminant is greater than 0 and f sub xx is greater than 0, then we have a local maximum. If d is greater than 0 and f sub xx is less than 0, we have a local minimum. Now, if d is less than 0, then we have a saddle point. Okay. So this discriminant, or this determinant of this matrix, right? We take determinants of matrices. This 2x2 matrix given by fxx, fxy, fyx, fyy is called the, I think it's Hessian. It's either Hessian or Hessian, I don't know. But the matrix of second partial derivatives. All right, on to, well, yeah, let's do some examples. All right. Yes. This is coming out of James Stewart's calculus book, 7th edition. The 8th edition is the most current, but I have the 7th. So if we have f of xy equals, let's see, e to the x cosine of y. Let us find local maximum and minimum values and saddle points of the function. So having the partial derivatives equaling 0 will tell us our critical points. Now, that's the same thing really as saying, well, so if the partial of f equals 0 at a point, and the partial of f with respect to y at 0, or equals 0 at a certain point, well, this is the same thing as saying the gradient of f at xy equals 0. So this, critical point. Critical point. All right. So let's calculate the gradient. F del f xy is equal to partial derivative of f in respect to x. Well, we treat cosine y as a constant and take the derivative of e to the x. So that's just e to the x cosine y. Now we take the partial with respect to y. We get negative e to the x sine y, because the derivative of cosine is negative sine. And we set it equal to 0. All right. So that means, well, 0 vector, right? Because the gradient is a vector. Now, we have e to the x cosine y equals 0, and negative e to the x sine y equals 0. And I'm going to ask, I want an answer to this. For what values of x and y do we have these statements hold? What values of x and y make the partials equal 0? Well, the range of cosine and sine is -1 to +1, but I think you're talking about the domain. Let's say all real numbers. Yeah. So, good question. Yeah. It doesn't matter actually. We could do 0 to 2 pi, just one period, or we could do all real numbers. Tell me from 0 to 2 pi, because I suppose that would cover everything else. So y equals 0 and 2 pi. Okay. So let's see. We have y equals 0, 2 pi. So let's do, and then x could be anything, right? That's what you're saying. X can be any real number. Because, the x, pi, okay. And you're saying like this. Okay, so we have 4 values for y, and then x can take on any real number, because e to the x we know is always greater than 0 for every real number x. Let's try this. So we have the gradient of f at any x value, comma 0. What do we get? We get e to the x cosine of 0, negative e to the x sine of 0. Okay, so this is e to the x times 1, and then sine of 0 is 0 times e to the x is going to be 0. Okay, well, if we do gradient of f at x and 2 pi, what do we get? We get e to the x. We get the same thing. We cosine 2 pi, negative e to the x, sine of 2 pi. Okay, so we get e to the x, comma, 0. There's 0 right there. And then same situation for x and pi over 2. We get e to the x cosine of pi over 2, negative e to the x sine of pi over 2. So we get this time we get 0, comma, negative e to the x. So it appears that none of these values are working, because I know this never equals the 0 vector. Why? Why does this never equal the 0 vector? Well, because e to the x is always greater than 0. Yes, always. Right? It's just that we don't have any y that we can plug in to make cosine equal sine equals 0. So yeah, like this, cosine of y equals sine of y equals 0 for no values of y. We can make one of them 0, but then the other one would be 1 or negative 1. Thus, what does that say? What does this tell us about the problem? We don't have any critical points. No values of x and y can make del f equals 0. So that means for every x, y, and R2, the gradient of f at x, y does not equal the 0 vector? Yeah, it's a trick question, right? That's why I wanted to bring this one up first, because we don't always have critical points. So in fact, we don't have any potential local extrema, so we don't have any local extrema. Good. All right, so that was a simpler trick example, but now we're on to going to a more difficult one. Let's see, which one should I do? Okay, well, yeah, this one's pretty tricky. This one's pretty tricky. So we have, let's see, show that f of xy equals x squared plus 4y squared minus 4xy plus 2 has an infinite number of critical points, and that d, the discriminant, equals 0 at each one. Then show f has a local and absolute min at each critical point. Now, this problem this is an animal of a problem, because one thing I forgot to mention, well, I suppose I can mention it now, didn't really forget, but so the discriminant, if we look back at the second derivative test, either has to be greater than 0 for a maximum in, or a less than 0 for a saddle point. So it has to have sign, S-I-G-N, not S-I-N-E. It has to have sign for us to come to a conclusion about the second derivative test. If the discriminant equals 0, well then what do we get? We get inconclusive second test, but you look at other methods to show that we have a local or absolute max or min at the critical point. So this means that inconclusive second derivative test. That's what makes it an animal. That's what makes it suck. Okay, so we have the gradient of f, right, equals 0 to find the critical points. So let's calculate the gradient of f at xy. We have 2x. This is a constant in x, so it goes to 0. And we have 2x minus derivative of this respect to x would be minus 4y. 2 is a constant. And then we have, let's see, respect to y, this would be 8y minus 4x. This equals 0 exactly when 2x minus 4y equals 0, and 8y minus 4x equals 0. So what do we get? We get 2x equals 4y, and we get 8y equals 4x. Well, in either case, both of these is just saying y is equal to x over 2. So that's where we get the infinitely many critical points. We get critical points all along the line y equals x over 2. So there's infinitely many points on a line. And now let's show that the discriminant equals 0 at each one of these points. In fact, since our function is polynomial of degree 2 in x and y, when we take the second derivative, that will eliminate every variable, so the discriminant will be constant. It doesn't depend on x and y. Here, I'll show you. So f sub xx, if this is f sub x, f sub xx is 2. F sub xy is equal to f sub yx is equal to, let's see. Well, if we take f and then differentiate with respect to y, we get -4. If we take this guy and differentiate with respect to x, we also get -4. So that checks out. F sub yy, that's 8. Because this is f sub y. We just do it with y again. This is 8. So there's no variable in any of my second partials, so it's independent of x and y. So discriminant is determinant fxx, fxy, fyx, fyy is equal to 2, -4, -4, 8. Okay, so we get, what do we get? We get 16, and then this is a triple negative, right? We have a negative times a negative, but also you subtract whenever you're doing the discriminant. So it's triple negative. We get -4 times 4 is 16. This equals 0 for all xy in R2. That's all xy of the form y equals x over 2 also. It works for all xy in R2. It also works on this line in R2 that we have the discriminant being 0. Okay, so that's not cool, right? Because then we're just like, whoa, what do? We don't have the second derivative test to work with anymore. So I'll tell you what we're going to do. It all lies back with our original function. We have f of xy equals x squared plus 4y squared minus 4xy plus 2. Now recall something I said earlier. See, the problem says show that f is local and absolute minimum at each critical point. So I'm going to write the definition of a local minimum. So let's say f of x naught y naught is a local minimum of f if for all xy in a neighborhood of x naught y naught, we have the following inequality. F of x naught y naught, the minimum, so that'd be less than or equal to f of xy in a neighborhood. Okay, so we're going to show this. Okay, so what's our x naught y naught? Our x naught y naught, well, if x is x, we have y equals x over 2 as well. So then we'll have f of x comma x over 2. This is equal to what? Well, you just plug in. Right, we have x is equal to x, so this is x squared, plus 4. Y is equal to x over 2, so we get x over 2 squared minus 4x, x over 2, plus 2. Okay? So then we get x squared plus 4x squared over 4 minus, and this would be cancel with 2, minus 2x squared plus 2. What does this equal? Okay, well this is 2x squared minus 2x squared plus 2. This is equal to 2. So that means all along the line in R2, y equals 1/2 x, we have a constant value of 2. I read 0. No, this equals 2. Yeah. Okay, so that means this just bring it all together. F of x over 2 is equal to 2. Okay. But looking back at our original function, we have f of xy is equal to x squared plus 4y squared minus 4xy plus 2. Let's rearrange this. We have x squared minus 4xy plus 4y squared plus 2. We can factor this. It's actually a perfect square. Look, x minus 2y squared. Because x minus 2y squared is really x squared minus 2y minus 2xy plus 4y squared. So we have x squared minus 4xy plus 4y squared. Okay, now what's one property of a perfect, a binomial squared? Well, x minus 2y quantity squared is greater than or equal to 0 for all xy in R2. So if this is greater than or equal to 0, and we're adding 2 to it, then this expression is greater than or equal to 2. If we eliminate y being x over 2, then we would have a sharp greater than, so we showed it. So we showed that f of x over 2 is equal to 2. And then this is less than or equal to x minus 2y squared plus 2, which is f of xy. Going back to the definition of local extrema. And since it's for all of R2, it would be absolute. All xy. Okay. So I'm going to go ahead and leave it there. I didn't get to everything I wanted to. Might bring it up next week. I had some cool problems. But we actually didn't get to absolute max and min. But for absolute max and min, I mean, the only difference is you draw your region in R2. Say it's a box. Right? So you just check. You would check critical points in the interior. Say this is region D. So you would check critical points in the interior of D, and then you would check the boundary of D. For instance, like if we had, f of xy equals x squared plus y squared. Well, you would just parameterize these lines, essentially. This line right here, you can present as x is constant 1 and y is a variable between 0 and 1. And then you would just plug that into here. And then you would do single variable calculus at that point. This line would be 1 or x comma 1, where x lies in between 0 and 1. You would plug it into here, then you would use single variable calculus. Okay. That's it. Is there any questions? You're welcome. You're welcome. I'll see you later.